Hi everyone, this is Mrs. Papadopoulos, and today I'm going to be teaching you about population dynamics. I'm going to change the style of this lecture video a little bit. I'm still using black as mandatory, blue is optional, but I've removed the outline format from today's lecture, which means that they're free-form notes. You can choose the organizational structure that works for you. If you'd like to return to outline format, feel free to use that. Start with capital letters, then numbers, then lowercase letters, and then Roman numerals. Look back at your previous notes to get a feel for how that works. Or go with something a little more freeform. Use diagrams with captions, use bullet points, use spatial organization, whatever works for you so that you'll end up with organized and complete notes at the end. Well, let's get started. So to talk about population dynamics, we have to start by defining two things. First, a population. This is actually a specific biological concept. A population is a group of individuals of one species that are all living in the same area. On the top, we have an individual pine tree and an individual clownfish. On the bottom, we have a population of pine trees and a population of clownfish. So one thing that I want to be careful about is that population, the word, is actually not just all of the clownfish in a particular area. It's the group of clownfish in a particular area that are breeding with each other, that are sharing the same resources, that are sharing the same mates, or competing for the same things with each other. Let me show you an example of what I mean. On the screen, you can see a map of bobcat populations throughout the Midwest United States. And a lot of students might see this and say, okay, the population of bobcats is every dot that exists on the screen, no matter what color it is. They're all bobcats, so they're all part of the same population. But that's not correct. What we actually see is multiple different populations. We see a green one, a purple population, a red, a yellow, a blue, even an orange population. And we call them distinct populations because they're only interacting with each other. The red bobcats are only interacting or looking among other red bobcats for mates. They're going to be sharing the same resources. They're going to be navigating through the same territory. Even though there's a little bit of overlap between the red, blue, and yellow, the red bobcats form a distinct population. Okay, so the second thing to define is another term that you're actually familiar with, population density. And you calculated this during your sampling methods week. This is the number of individuals per unit area. And on the screen, you can see two examples of human populations that have very different densities. On the left, we have a high population density, many individuals packed into one area. And on the right, we see a pretty similar geographic area. It's a pretty similar space that you can see in both pictures, but on the right, we have far fewer humans in that same area. So this is our low population density, okay? We'll return to this concept a little later. So let's put this lesson into context. How would you determine the population size of these different organisms? A pack of wildebeest, or all of the wildebeest across the African savanna. We're looking at snow leopards, or different grass species. We might be looking at different fish species. You've used whatever sampling method works for the situation to determine the size of a particular population. What if we're tracking that population size over time? If we run a sampling experiment over a long time span, we can see how the size of that population changes. So you may have used your tagging methods, your trapping methods, mark and recapture, quadrat sampling, transect sampling, and you've done that over time. So now you have a data set of a population over time, and you can see when it grew, when it decreased, and you can make predictions or analyze that data. So this is what population dynamics is all about, how a population changes over time. And we can represent population change with an equation. It's in black on the screen, so make sure you go ahead and write it down. And this is an important equation, so you're welcome to put a box around it or use highlighting or underlining to make it stand out on your paper so that it's easy to find later. Population change is equal to births plus immigration minus deaths plus emigration. Let's actually define each of these terms, even though I'm sure that you know what some of them mean. Underneath the equation, make sure you define them. Birth. Birth is the number of animals or individuals, we can generalize it, the number of individuals born into a population. And I put the word into in all caps because I want to remind myself quickly that births add to a population. Deaths are animals dying out of a population. Immigration is the movement of animals into a population, or the movement of individuals into a population. So immigration also adds to a population. And lastly, emigration is the movement of individuals out of a population. So emigration and deaths remove animals from or individuals from a population. Okay, if births are greater than deaths, then the population would be expected to grow. We'll be adding more animals or individuals than we were removing. But if births are less than deaths, then the population will decline because we're removing more individuals than we are adding. So let's do some sample math problems. And here's some information that you had before, but we're actually going to write down a equation that's not extremely different to the one we just wrote down. It's in a slightly new form. So I also want you to write this one down as well. A new population, so not population change, but a new population is equal to our initial population plus births plus immigration minus deaths minus emigration. And we're going to do it in that order. New population equals our initial population plus births plus immigration minus deaths minus emigration. And here's an example. This example is going to come up in blue. A population of birds in a forest starts at 100 birds. During 1 year, 12 baby birds are born, 8 old birds die, 4 birds move into the forest, and 6 birds move out of the forest. How big is the bird population at the end of the year? So we're going to use our equation. New population equals initial population plus births plus immigration minus death minus emigration. Our initial population, so let's plug in our numbers. Our initial population is 100. Our births are 12. Our immigrants are 4. Our deaths are 8. And our emigrants are 6. So when we plug all those numbers, 100 plus 12 plus 4 minus 8 minus 6, that will equal 102 birds. So we grew by 2 birds because our new population is 2 more than our initial one was. So our population grew a little bit. Let's look at another example with fish. This part's in blue, so you just need to read it, but then we will have a question in black. And this time I do want you to write down the example question, and the calculation will also be in black as well, so make sure you write that down too. Okay, a population of sturgeon, that's this fish species that you see here in the picture, in a lake starts at 100 fish. During 1 year, 50% of the population successfully reproduces. Each pair has 2 offspring. So that means 50% of the population has 1 baby, and 10% are eaten by predators. The pond is closed off, so there's no immigration or emigration. How big is the fish population at the end of year 1? Okay, here's our same equation. New population equals initial population plus births plus immigration minus death minus emigration. All right, so we got to do some calculations before we can plug in our numbers. Births is going to be 100 times 50% because 50% of our fish are replacing themselves or they're having a baby. So 50% of our fish is going to be 100 times 0.5 or 100 times 50%. So that's going to be 50 new fish are born. 10% of our fish are dying because they're eaten by predators. So 100 times 0.1 or 100 times 10%, that's going to equal 10. We have no immigration and no emigration. So let's now plug all of these numbers into the equation below. Our new population equals our original 100 plus our births, 50, minus our deaths, 10. There's no immigrants and no emigrants. So our new population is going to equal 140 sturgeon fish. Follow-up question. If we end year 1 with 140 sturgeon fish, how big is the population at the end of year 2? Same conditions, 50% successfully reproduce, 10% are eaten by predators, but now we're looking at year 2. Remember, the population at the end of year 1 was 140 fish. So we're going to have to use this as our new initial population. And here's our equation again. before we plug in our numbers, we have to do some calculations. So our births is going to be 140 times 0.5, or 50%. So we have 70 births. Our deaths is going to be 140 times 0.1, or 10%, and that gives us 14 deaths. Still no immigration and no emigration. So now we can plug in these numbers, and our year 2 population is going to be 196 sturgeon at the end of year 2. And you might notice that we increased by 40 in year 1, but now we've increased by 56 in year 2. So we've added even more fish. Let's keep going for 15 years. This is going to be in blue, so it's optional to draw on your paper. My T-chart is going to go all the way down for 15 rows. So it might go down pretty far on your paper if you're going to draw it. Okay? On the left side of the T-chart, that's going to represent year, and on the right side of the T-chart, that's going to represent the population size. And again, we're going to be numbering our years from 0 down to 15 because I'm going to track this for 15 years. In year 0, when we started, we had 100 fish. At the end of year 1, we calculated that we had 140 fish. At the end of year 2, we calculated 196 fish. So if we continue the same calculations that we just did on the previous slides with the same conditions, in year 4, we would have 274 fish. Whoa, we added almost 100 fish. At the end of year 3, we would have 274. And at the end of year 4, we would have 384. At the end of year 5, 538. So between years 4 and 5, we actually added over 100 fish. Notice how we're adding even more fish every single year. At the end of year 6, it would be 753. At the end of 7, 1,054, then 1,476. Whoa, we're adding more than 400 fish in 1 year now. When we started with only 100, well, now things are increasing pretty quickly. At the end of year 9, 2,066. At the end of year 10, 2,893, then 4,050, then 5,669, then 7,937, 11,112, and at the end of year 15, 15,557. So between years 14 and 15, we added about 4,000 new fish. Amazing. And if we turn this T-chart, this data set, into a graph, which you're welcome to sketch, it's optional, on the side of your T-chart, it would look something like this. Our population starts very small, and as we go and extend that population over time, here's year 15 all the way over here, and we look up, we get about 15,000 fish. Let's say I extended this all the way to year 20. By then, we would have up to 75,000 fish in 20 years from a population that started at just 100 sturgeon fish. That's an incredible increase. Here's the claim that we can make about this data. Over time, the sturgeon population increases, and each year that it increases, it will increase even more than the years before. We added 40 fish, then 56 fish, then almost 100 fish, and by the end, we're adding almost 4,000 fish in a year. This type of growth, now it's in black, you've got to write this down, is called exponential growth. This is a really important term, and I've underlined exponential growth. Feel free to make this stand out on your paper. Exponential growth is when a population's growth rate stays the same regardless of population size, making the population grow faster and faster as it gets larger. And I know it sounds contradictory to say that the growth rate stays the same, and yet our population is growing faster and faster. But if we think about the last example that I just went over, our growth rate stayed at a 50% reproduction rate and a 10% death rate throughout all of the 15 years that we calculated things for. So that growth rate never changed year to year. And if those two numbers stay the same, when we get to larger and larger populations, we see that the population size is growing faster and faster. And so we'll end up with a graph that looks like this, curving upwards, getting faster and faster as the population size gets larger and larger. However, you might have started thinking about that sturgeon population, and maybe you wondered, is our fish pond really big enough to hold 75,000 sturgeon in 20 years? Will we actually have that many? Is there enough space? Well, no, we won't. Exponential growth never happens forever. Eventually, the population will run out of something, space, food, etc., and the growth rate will slow down. At that point, our graph will transition from an increasing graph to something that levels out. We start off with a quick increase, looking at this one, there's a quick increase here, but then over time, and as that population size gets larger, the growth rate slows down until it levels out. So even though I say a population's growth rate is getting smaller, I'm not saying that the population size gets smaller. The population is still increasing in size. We can see that our graph is still going up, but the population will eventually approach a maximum level, and then it's going to stabilize at that maximum level. And this type of growth is called logistic growth. When a population's growth rate gets smaller and smaller as the population size approaches a maximum. So here are our two types of growth, exponential growth on the left and logistic growth on the right. What you might notice is that they are connected. Exponential growth is just the beginning of logistic growth. Logistic growth starts out with exponential growth, and we can see that happening right about in this portion of the graph. So here's our exponential growth happening. And then logistic growth will begin. It's going to transition to logistic growth around this portion of our graph. And then as our population size is getting larger, it's going to start being limited by something. And the growth rate is going to slow down until our population stabilizes at some maximum. So why don't population sizes keep increasing exponentially? What factors influence a population size? Well, those factors that influence population size, like I mentioned before, space, food, resources, etc., those are all called limiting factors. A limiting factor is something that limits the growth, abundance, or distribution of a population. Here are some examples. Food availability. How much food is there in the environment? Space availability. Can we expand? Is there enough room for us to exist? Disease. If a population is really abundant, it may actually experience higher rates of disease because there's more hosts for the disease to travel through and spread through. Competition for resources or mates. If a population is really small, it might not actually have a lot of mates around. And as the population grows bigger, now there's going to be more mates available. But also, as our population gets bigger, there's going to be more competition, not only for mates, but for other resources as well. And they're going to be competing for those more fiercely at a larger population size. Predators. The presence of predators will limit the size of a population as well. And a natural disaster or climate change. Those can limit the size of a population too. A natural disaster like a hurricane could wipe out an entire population. As climate changes, an area might become too hot for a population to survive. So these are all examples of limiting factors. But we can actually group these limiting factors listed here into two groups. And it's going to be based on their effect that these two groups have on the population, and it depends on how dense that population is. So on the left, we have a high population density, and on the right, we have a low population density. Some limiting factors will affect these two regions very differently. So for example, which area would we expect to have more competition for resources? Definitely the one on the left. So competition for resources will affect these two areas differently. They might feel it in different ways. However, there are some limiting factors that will have the same effect on these two areas no matter how dense the population is. For example, if it gets too cold or too hot for humans to live, both of these areas are going to feel the effect of that temperature equally. It doesn't matter how large or small your population size is, the temperature is going to affect them all in the same way. So that brings us to our separation. I've highlighted in blue the top 5 factors that we listed before. What I would recommend is putting a bracket like this around them so that you can see that those top 5 factors are all grouped together. The top 5 factors are what we call density-dependent factors. These are factors whose effects on the size or growth of a population vary with the population density. They affect a high and a low density population differently. And we talked about competition for resources already. That's a really easy one to understand. A dense population will have way more competition for resources than a spread out population would. But a dense population will have much more mates available more easily than a spread out population would. Disease. Disease is going to affect a dense population more than it would a spread out one. It'll spread through the dense population faster. Predators. Predators are going to be able to find food in a dense population more quickly than in a spread out population. Food availability and space availability both have to do with density because a dense population will have more competition for food and space than a spread out population would. Okay, and what about our last one? Natural disasters and climate. These are in their own group called density independent factors, a factor whose effect on the size or growth of a population does not change with the population density. For example, if a certain area becomes too salty for freshwater fish to survive in, all of the freshwater fish will have to move out of the area or they're going to die. And it doesn't matter how many freshwater fish there are. It doesn't matter if the population size is large or small. They're all going to be impacted by the extra salt equally. So this describes a density independent limiting factor. Putting all of our limiting factors together, we can understand something called the carrying capacity of an environment. The carrying capacity is abbreviated as capital K. This is the maximum number of organisms that an environment can stably hold. Now, I put the word stably in bold, and you should underline it or do something to make it stand out because it is that important. It's not just the maximum number of organisms that we can squish into a place. The carrying capacity is the maximum number of organisms that can survive in a location year after year, reproduce, die off, refresh themselves, emigrate, and stably stay around that same maximum. There's 3 things that we need to know about the carrying capacity. Number 1, the carrying capacity depends on the organism and the environment. Different organisms within an ecosystem will have different carrying capacities. When we look at a food web, we're going to have one carrying capacity for our tertiary consumers and a different carrying capacity for our producers. Number 2, we can estimate our carrying capacity through population size data. And I'm going to show you how to do that when we look at some graphs in a moment. And finally, number 3, carrying capacity can change as the environment changes. So I'm going to show you a graph with the carrying capacity marked in a moment, but this is my test for those of you who should be listening. I do not want you to draw the graph that I'm going to show right now because I'm going to have you draw a better one on the next slide. So what I show you right now is not the graph I want you to draw. The graph that I'm showing right now, we can see logistic growth. So at the beginning, we're starting out with our exponential growth, and then our population growth rate is going to slow down until we stabilize at a particular level. And we've marked this level that they stabilize at as the carrying capacity. So we found where the population stabilizes, and then we draw a horizontal line that reaches all the way to the y-axis. And wherever it hits, whatever population size it hits on the y-axis, that is what we're going to label as the carrying capacity value for this population. So we saw this population grow and grow and grow until it stabilized around a carrying capacity. But the reason why I'm not having you draw this specific graph is because this one right here does not really represent reality. In reality, populations are never going to show us this beautiful, perfect stabilization where all of a sudden the population size stays exactly the same forever. It's impossible. What we're really going to show is something more like this, where we see exponential growth, and then as our population approaches a carrying capacity, which is now marked in the red dotted line, it overshoots the carrying capacity. And as it overshoots, what does that mean? Now there's too many individuals and there's not enough resources to support all of them. So some are going to die off and we go below our carrying capacity. So that's happening right here. Too many individuals, not enough resources, so we have a die off. And when they die off, we see that our population size is actually going to undershoot the carrying capacity. It's going to go below the carrying capacity. But now that the population size is below the carrying capacity, that means there's more resources available for those who are alive. And so what happens to those who are alive? They're going to reproduce, and they reproduce at a higher rate. And so that's going to cause our population size to go back up. And we're going overshooting the carrying capacity again. So we're going to imagine if it overshoots the carrying capacity again, there's going to be another die-off. And so now we're going to have a cyclical pattern. It's going to repeat an overshoot and an undershoot, an overshoot and an undershoot. Okay, so our graph, once it reaches the carrying capacity or approaches it, we're going to see fluctuations. The population size is going to start fluctuating around our carrying capacity. All right, so this is the graph that I do want you to draw on your paper next to where you wrote the definition for carrying capacity. And I'd like you to sketch this wiggly green line. Make sure you label the part that shows exponential growth, just like you see here. Make sure you are including the red dotted line around the center of the fluctuations, and we're going to label that the carrying capacity. I'd like you to draw your axes, your y-axis and x-axis, and make sure you label them. Our y-axis is going to be the population size, and your x-axis is going to represent time. So go ahead and sketch your graph on your paper right now. There's two more things that we need to know, and this is going to be a summary of the graph. Grown populations typically overshoot and undershoot the carrying capacity. That's what you see in our peak values and our valleys. So here's an overshoot and here's an undershoot. And here's another way of saying that sentence. Growing and stable populations fluctuate around the carrying capacity. So these ups and downs, this repeating pattern of going up and under the carrying capacity, that's called a fluctuation. Most ecosystems have established populations fluctuating around their carrying capacity. So here's a real example. A song sparrow population in its natural habitat, and you can see how its population is fluctuating over the years. Now, if we had to estimate where the carrying capacity exists here, I would draw a horizontal line in between most of the fluctuations. And if I did that, it seems like it's around here, the middle of the fluctuating pattern, it would be around 35 sparrows. So that's my carrying capacity that I'm estimating for this population, 35 sparrows. Here's another example. We have two populations fluctuating. We've got moose in red and wolves in blue. And this actually shows one of the reasons why population sizes fluctuate at a carrying capacity. As we get more moose, the wolves who eat them are going to start eating more moose. They're able to, and once they're eating more moose, they have more energy for reproduction. And so the wolves are going to reproduce at higher levels because now they have more nutrition. The wolf population is going to peak until they've eaten too many moose. And we also see the moose population is going to crash because they're all getting eaten. And as the moose population crashes, well, now there's too many wolves around and not enough moose to feed them. So our wolf population is going to crash as well. And we won't really see that crash until sometime after the moose population starts declining. So that's why we see a lag between the decline in the moose and then a decline in our wolf population. And as time goes on, this pattern is going to repeat where the moose population will grow back, and that's going to cause the wolf population to grow back. And then as there's too many wolves, our moose population is going to decline, and then that's going to cause the wolf population to decline. So they're fluctuating, and they're going to actually fluctuate in some kind of an inverse pattern. So this is showing a predator-prey relationship. And since in our ecosystems we have established food webs where organisms are eating each other, we see population booms and busts, overshoots and undershoots, fluctuations, as different populations take advantage of the resources and then die off as those resources become unavailable. and then take advantage of the resources once they're back up. And then there's a die-off again. But we will see new growth in some interesting new populations. Okay, now there are some cases where new populations do show exponential growth. And so here I'm going to show some examples where you might see exponential growth instead of a fluctuation around a carrying capacity. You might see exponential growth when bacteria colonize a petri dish. That exponential growth will eventually transition to logistic growth as the bacteria run out of space or food. The introduction of an invasive species. When we introduce an invasive species to a new area, it's got unlimited space, resources, and habitats. It's going to grow exponentially until it reaches a maximum. A new virus spreading in a population. There's a new population with a ton of hosts available, unlimited resources. It can reproduce wildly, exponentially, until it reaches a stable maximum. And lastly, a reintroduction of a keystone species, like the wolves to the Yellowstone Park. That wolf population starts off really low as it's reintroduced. And then as time goes on and they reproduce and reproduce and reproduce and take advantage of all the resources and space that are available, they'll grow exponentially until they reach that stable maximum, at which point they are going to transition to logistic growth and then likely fluctuate around a carrying capacity. All right, final section. What impacts the carrying capacity of an environment? Well, a bunch of things do. Resource availability is one, habitat availability is another. If any of our limiting factors change, think back to the list that you wrote down earlier. Predators, for example, was a limiting factor. What if all the predators are wiped out by a disease? Well, now our carrying capacity is a lot higher because you can support more individuals now that there's fewer predators. And humans. Humans can change the carrying capacity. Human disturbances like climate change or deforestation or lack of food, all of these things can impact the carrying capacity of an environment. Here's some examples. Carrying capacity can increase if there's more space available for growth. If we transfer our bacteria into a larger petri dish, the carrying capacity of the environment changes because there's more space to support them. Or an increase if there's more food available for animals. Let's say there's extra rain one year and our acorn population is extremely high. Now, with more acorns, the carrying capacity for animals in that year alone is higher because there's more food available for them. On the other hand, carrying capacity can decrease if deforestation decreases food or habitat space for animals. If we cut down a bunch of forest, we've lost all of the habitat spaces for the animals that live there. And it can also decrease if in our coral reef, climate change kills a bunch of the corals because of rising temperatures in the sea. With all of that dead coral, we have loss of available habitat for animals. So same deal. One of our organisms dies or is removed by humans or climate changes, and some organisms die as a result. That's going to decrease the carrying capacity for anybody that relies on that thing. So here we've got, in our bottom example, we've got a density independent factor killing our corals. That's the water temperature. And as the water temperature gets higher, it will impact all the corals equally, regardless of how many coral there are, if the population size is dense or not dense. So it was a density independent factor that basically killed all of our corals, brought our carrying capacity for coral down to zero, and then impacted the carrying capacity for all of the organisms that live in the coral reefs or use the coral for something. Now their carrying capacity is much lower because they might rely on the living coral for some of their needs. And so that would be a density dependent factor because those fish are now going to be competing with others for the limited live coral or limited intact habitat spaces that are still available. Okay, so this was our lecture on population dynamics. I hope you enjoyed some of the complex interactions we see, and I hope you've made your graphs beautiful and that you'll use these notes for the rest of the week.